We have Andy now. A little bit of intro about Andy. Andy is one of the leaders at the with the PyData community. He's the founder, one of the founders of Anaconda, and he's also been the founder of NumFOCUS, and he's currently a CUDA product, a Python product manager at NVIDIA. So over to you, Andy, to present about building inference workflows with Terrel languages.
All right, thank you very much. Hi, everybody. So I gave the committee two talks, and they said they wanted this one, which is going to be lower level than anything here at the conference. So I'll try to bring it a little higher level, but fundamentally we're going to be talking about hardware and some of the challenges you get to programming that hardware. So I'm working on a new product that helps you use tiles. For folks who've maybe been around the inference game, how many folks have heard of Triton or TVM or things like that? So it's in that family of languages. I'm not going to talk about those languages, but a lot of the principles we show are across all these different these languages. But just to kind of set the stage, so DeepSeek, this was our big announcement when DeepSeek came about, right? So open source reasoning model leveraging our accelerated computing platform. Look here, we have Hopper, which was our flagship card at the time, FP8 tensor cores, these transformer engines, and on top, and that was just the GPU itself. Underneath, we have things like our networking switches and our links between things and our own protocol across the wire. So other technologies are involved, we have amazing chips, then you have the switch layers, and then at the bottom, we have our CUDA libraries, Cutlass libraries, and things like NVSHMEM and things like that. And so DeepSeek was able to use all these things to produce the best model, 671 billion parameters at the time. Now, fast forward 18 months later, we've now announced that we've won the Inference Max benchmark. And we did that. We're 15x slower cost per token. So that's H100, that was the Hopper, that was the gray line. And today we're at GB200, Grace Blackwell. So we re-architected both the CPU and the GPU. And we're getting 15x. This is so important because AI is taking over our world, right? AI is becoming the workload. You hear everyone talking underneath what they're talking about, this agent or that agent. They're calling these models. So it's critical that we get them to be much more performant than they are. Even now, I think I read somewhere we're going to run out of power in next year or something, ways to produce power even. So we're going to be limited by how much power can we even get the industrial complex to produce to run AI models. So while we got 15x slower per token for this one model, we really need to expand to all models. We need more performance for everything out there or every token that gets generated. And right now, Blackwell, which was announced 2 years ago, really started hitting the market last year. You can get them today in mini form, so the Spark NVIDIA Spark that sits on your desk, looks like a little Mac Mini. But right away, it's a different architecture than the Hopper was, than the Ampere was. Things that kind of brings along with it, 2x more throughput on data types like FP16, int8, FP8, TF32. These are data types these are not pandas data types anymore, right? So now we're getting down to fundamentally different ways of getting to smaller bits of data. And that's important because to get those models to be faster and more cost efficient, you need to move less words. The most expensive thing on a computer is to move memory move a bytes from memory to your GPU or to your CPU. Throughout the last 15 years, the more memory you have to move, the slower you're going to go. So what we're doing, we're going to smaller width types in order to get to that precision. Next, we're doing mixed precision things. The researchers are all into this block scale type support for mixed precision. So if continue that theme of can I get smaller and smaller precision so I can scale these inference models. Then the next one, we're expanding the tensor core into 2SM. So we're making and I'll talk a lot about this, but the new type of core that came out in Volta, which was, 8 years ago, is now expanding over not just one SM, but more of the streaming multiplexes. And we're giving a fully autonomous tensor core programming models. The second big thing, so our tensor cores are changing. Our cores are changing fundamentally. Second big thing is changing. Our memory hierarchy is changing. We now have tensor memory. So previously, you would have shared memory going to your SMs. Now you have tensor memory going to your tensor cores, which are the better tensor cores for over Hopper. And this has new scheduling capabilities, such as thread blocks and things like this. So fundamentally, the takeaway from this slide, the hardware is changing a whole lot. How many people are changing their programming style yet? Right? No one. And I always tell my colleagues, only the top six inference companies in the world are doing this today. And my mission is to help everybody else get the power out of these chips that those companies can. So that's what this talk is about. How do we get the power out of the Blackwell and the newest chips? And if you think about GPUs, they've evolved over time. In the 90s, they were fixed function accelerators. They did a few things, and they did them really fast. Then there's like the 8 modes of DirectX and things like that, where like this, if you could program these 5 or 6 functions, we could do it really fast. Then we brought out programmable shaders. Programmable shaders brought a lot more support, and the games just blew up, right? And that's when regular programmers actually started caring, once they could actually program these things with arbitrary code and build their own systems. And that's where the Brook project came up that then developed a unified structure that became CUDA. It allowed us to program a GPU as if it was a regular Turing machine type computer, and looks like you can do any sort of things the languages can do. And so kind of going through all that, we get more and more to something general purpose that people can use. And then now today we're in the AI accelerator world. And AI accelerators, just like the TPUs out there, the MPUs and all these things, they really function on making tensors go like tensor operations, matrix multiply accumulates, operations that work on full tensors all the time, work really fast and stream through those. And now we're in the world where you have to use the tensor cores, you have to use specialized memory to get full bandwidth out of these chips and full efficiency. So what does that look like? Well, just to give you a really high-level cartoon view of a GPU, so CPUs, which everyone's going to program to, you'll have a few of them on a chip. They get bigger, you might have, I think our ARM core has 70 chips, but you have a GPU which usually has thousands of chips on it. And they're smaller chips, but their threads are implementing in a different way. But fundamentally, you get a lot more chips or a small number, with the difference being that a CPU is always going to run, it's going to be able to address a lot more memory. It's going to have a pipe that is to that memory that's pretty thin, whereas GPUs is going to have a lot faster memory, usually a lot less. So if you can't fit it in that memory, it's usually going to be 10x the speed is, where a CPU can always hit more and more memory, and you can do things like that. GPUs are going to have a fixed bit of memory, and you're going to have a bigger cost if you get off that. So feeding these things, now I might have 10x more lanes to my registers on a GPU, but I have typically 10 to 100x more processors to feed. So your algorithms have to be fed in a way that you can load a bunch of data, do a lot of work, and get throughput out. And we like to say that CPUs are latency bound, GPUs are throughput bound. So if I'm going to take a bunch of people downtown, if I put them on a bus, I can get a lot of them there at once. But if I put them all in cars, they're going to be getting there arriving, they'll eventually all get there, but they don't have the luxury of like going to on a bus. You don't have the luxury of doing anywhere, any direction you want. You have to all go together. So the big difference between CPUs and GPUs. So we can think of like two ways to hit GPUs. First is like a grid level where you take the system that will divide your code into blocks and tiles and map it onto the hardware. So for example, if I take CuPy, which is just a NumPy implementation on a GPU, and I say I take some samples, I sort them, I do cumulative sum. Underneath this system, CUDA libraries will automatically grid that up and split it up and run it on all those cores. But then there's the thread level where I get to control every single one of those cores. And you write a CUDA program, you can see here, I specify what grid and what thread I'm using, this is based upon a hierarchy where I have blocks, grids, and threads, and then from that I can actually give that particular thread its bit of work. And I'll synchronize between arrays and so forth. You can see how like sync threads and so forth. And like all the threads that get launched, and they get launched in groups. The groups are called warps, but they get launched as a group, and we schedule them throughout. So you can have a lot more threads, virtual threads, than you do on the chip, but it does kind of map out so that you're having the thousands of threads hit the 1,000 cores all at once. And you have maximum control. And really, so one side grid level, I don't have to worry about threads. Other side, I have to manage every single thread. So in the middle is where we're missing bit, because like I said, you have to have tensor cores, you have to be using a lot more blocks, you have to be able to use everything in a tensor together, and we'll talk about what's missing in the middle, and that's where the tensor core came. So the tensor core was released in Volta. Originally it was like 8 threads doing dgems, basically, doing small matrices multiplies. And now Ampere came up and used a whole warp, so the whole group of threads. And now it's using 4 warps, and Blackwell's, as I said, even more different. So each one of these iterations, you're able to use different streaming operators through your memory in order to program these GPUs. And it's great for inference problems. So you can take your inference problem and outline it in MMAs, and we'll go through like how you do this with softmax here in a minute, and get full use of the card. Now, what this means is that you've changed from, like I said, there's execution, there was blocks, threads, or groups, which we call warps, and then threads. And now we're saying, for maximum performance, everybody who's going the inference route will use blocks. So we think of like the execution being at the block level, and you don't have to worry about the individual threads. The data elements, no longer am I going to go get a single index, but I give you a block of those indexes. And so I just say, all right, you're given A, you're given B, and you get that whole block out of it. And so that, for what we want to do there, so, and generally this is what you had to do to create CUDA programs to begin with anyway, so you split your work into tiles, and now you give the tiles to the operating system. Now, even if you're going to do that to map onto tiles today, there's a lot of things you have to think about. So if I'm going to store my tiles, I have registers, I have S memory, and I have the tensor memory. And which memory is that particular thread going to be using? It's up to you. You also have memory layout. So one of the pieces, probably people learn about row, column, form, row major, column major, and then we have like a swizzle kind of style here as well, because if you want to get the closest memory to your execution, you're going to have to be able to do your memory layouts. And like there's lots of different memory layouts you could come up with. There's all sorts of crazy linear combinations, and those sorts of things have to be managed by the programmer in the thread world. On top of that, you've now got 3 types of memory to manage, but you also have, do I synchronize, do I do something asynchronous, or do I block asynchronous? And so at what point do I transfer memory becomes kind of difficult to understand as well. And then finally, like, how am I going to block, what is the compute? Who's going to actually compute this actual ID or this index into it? And there's a bunch of different ways people do this, and this is what people work on in inference pipelines constantly. So just reiterate, today in the thread model, you have to make this transition from a grid level to a thread level through tiles, split my work into blocks, manage my memory, manage my compute strategy, my tile layouts, and my storage. The next level of languages are looking to take all of the technologies, not away from you, but like allow you to do it, allow the system to do it for you. And so the newest level of compilers that we're releasing is able to take all these memory management strategies and compute strategies and put it into the compiler and teach it how to block up your data on a GPU. So why do we do this? Why do we enter a new model? Well, number one, we want to simplify your code. Like we have a grand challenge of getting AI inference to scale without destroying our environment. We want to be targetable from any language. We don't want just C++ and Python folks, we want Rust folks, Fortran folks someday. Everybody should be able to go to this level of blocking up their algorithms rather than just having to only a few select companies be able to do that. And we want a stable abstraction. So as you notice, these tensor cores are changing warps, but they're also changing the type definitions, the throughput of each type, and so forth. And so we really need something to help programmers handle that evolution. And I think this is sorry, I'll skip that slide. So what we're introducing is a new programming model for CUDA called tile programming, or CUDA tile programming. The compiler, the tool is QTile, which will be released hopefully within the next month. So we'll be pushing out the announcements and whatnot. So check in. It was, I'm not allowed to allow states, but it's very soon. Just say like with it, I could show you it working on a DGX box if I had it here with me, but I don't have it one of those today. But it brings that block level model to target that productivity so that applications can map to data, and then the compiler maps those blocks onto the threads. Okay, so you don't have to worry about exact MMA instructions and so forth anymore. Now, we totally are stealing everything from NumPy here. So we're operating on arrays or tensors, just like NumPy did, and giving you a programming model that you work on arrays, not individual threads anymore. So this should be really well suited for regular data parallel problems. And it also simplifies to like other implicit uses of threads and so forth. So you can think about if I had a tensor addition, I could have the same idea, map it back up to an array mapping. And so even there, you take your old code, SMT code, and bring it up to a tile level, and then our compiler is going to be able to schedule it and get maximum performance out of our chips for you. So now, so this is some of the same things they said. Like this is really taking a Pythonic approach to GPU programming. The programs will have a single logical thread per block, so you don't have to think about a thread, all the threads being launching at once. It's like I give it a block, and then I'll have a sequential order of the language through there. Operations are cooperative, so one of the things we're showing, like those tensor operations that used to take only a couple of threads, and now it takes a whole block of threads, and now it's going to take multiple blocks of threads. So threads actually have to talk to each other and cooperate in this model. So you don't have to manage that yourself anymore. You don't have to sync threads exactly on the boundaries like we did in that first DGEM. The compiler will figure those things out for you. And you can see here, like here's a softmax function in NumPy, and then a kernel for a GPU in QTile. So the only difference here, if you squint closely, and folks in the back, sorry, usually we have a higher screen, but the only difference here is my tile, I have a little bit of syntax to load the tile and store the tile out. So kernels are launched on a device, so you don't have the same control of memory, so we don't return back in a kernel, we just load back to memory. So we load from memory, we store back to memory. And so in this, I'll take a max, take my exponentiation, sum over my all my various samples and then do the normalization to get my softmax. So this piece of code right here works both NumPy. Now you add a few things in here into QTile, and this runs very fast. We'll show some numbers in a minute. In addition to QTile, so QTile, the programming model, the tile idea, QTile, the actual implementation of Python. We're also giving folks the QTile IR, which is a virtual ISA. So for folks, an instruction set architecture that the compiler takes in not just Python, but you can actually build your own compiler. So you can play around with this new abstraction and you implement other things on top of it. We're providing plugins for things like Triton as well, and we've seen really good performance where Triton was able to use this implementation and get on all of their inference systems a faster version using all the features of Blackwell. And it's also designed as an open source MLIR dialect, so it'll be open at some point. I think they're going through the specification process now. So this is a standard we're putting out for the world to see and program to. So, and there's a kind of a compilation path. If folks have questions, we can dive deeper into that. But let me just show you, so just to show you how powerful it is, here's a naive CUDA-Python SymT. I think I showed this a little bit to you earlier, right? That was lines of code, the terrible metrics for complexity, but it's one of the best ones we have. So you can see, even that thing I showed you, that thing's going to get a lot more performant than if you wrote on a CPU. Here's the QTile version of it. We have what's called a partition view in this case. So instead of just loading a particular tile, I can say, give me different partitions. And so there's an offset. So if I have my data space, I can say, give me the tile above me and the tile next to me and so forth. And we have a partition view system for that. And then I just write out my ct.mma, which is just the matrix multiply accumulate, and that forms my map mole. To do the same thing in what's the fastest the state-of-the-art implementation today. Oh, I hit the wrong button. Okay, all right, there we go. Looks like more like that. So if you go into Cutlass in C++ SymT, you're going to get a lot more lines of code to do the same thing. And this because this code is going to do warp specialization. It's going to have certain things transferring memory in the middle of while other things start pre-computing and so on and so forth. That schedule and layout's all taken care of for you by the tiling compiler. And we will have a C++ version early next year, but no one in this room has to use it. So just go through some examples. I showed you the softmax. This provides the idea, right? The global arrays so I have my I comes in as a global array with an immutable logical access to logical blocks. And so I access this thing through a load. And there's different syntax of which part of this array system I'm going to load. And then I can have the different shapes and index into it on the second dimension as well. Global arrays are mutable and accessible by all logical blocks. So any block can kind of come in and store back to your block, and the compiler will do the dependency analysis to schedule it out correctly. Arrays are immutable in the sense that everything returns a view, or returns a copy and not a view, sorry. It's an important thing to get right. So if I call a transpose there, that's now a copy, not a view. So we do differ a little bit from some of the NumPy decisions, but then I can store back. So if I do some operation like a transpose, I still have to store back, so onto my memory systems. We'll have uniform launch APIs. So the kernels are launched at the same underlying APIs as like the SymT kernels. So you will be able to call these, if I have a bunch of SymT code, I can call a tile kernel in the same program. Today you can't call the tile the tile compiler can't handle if you're calling SIMT kernels or from tile or vice versa, but if you're calling it from the program on the host side, we can launch in the same program. We have some improvements to make. So yeah, and you can see the self-contained, completely free of any TMA descriptors, so you don't have to tell me your memory went to the tensor core or anything like that. We'll manage that for you. And the CAI things I think are less important. Now you can write CUDA SIMT. This is what I just said. I could write this vector add as a SIMT. So this CUDA JIT with our numba CUDA implementation, which we'd use for each thread. Like I'd pull out my thread ID and run it there, or I can run it as a tile computation where I load my tiles, then do my calculation and store back. And this can be called from the same program. Matrix multiply, it's the same idea as well, where we're able to pull out the loads and stores and sum over the MMA. So you can lower it to MLIR here. This is actually a tiled matrix multiply compiler, and so I can take just a number of tiles as opposed to going over the entire, like the indices of the range and chopping it up myself. I'm low on time.
7 minutes from now.
Okay.
The talk, and then 5 more minutes for questions. Or we could start questions earlier.
Sounds good. But you can see how I run the blocked tiles through, so I'm no longer in the blocks per se, or on the threads, and I get that MMA instruction. Now, of course, and then the store back, which I've already gone through. Of course, everybody asks us, how does this look? So comparing to our state-of-the-art baseline here's 4 kernels inside your inference. So your gems, your fast multi-head attention, forward multi-head attentions, and then some decoding MLA operations. We're already seeing ourselves beat cuBLAS and cuDNN in specific operations. Now, the power of this is that because it's a language, as we add new data types, as we add new operations, we can just change the language and the compiler will map to the correct operations under the hood. Whereas our state-of-the-art libraries and the libraries in many corporations, you have to reiterate and write these things over and over again. And so this is my last slide. So we have cuTile IR, we have cuTile coming out, then we have and this will be, within weeks, we'll have all this on GitHub. So look forward to seeing that. Then on our roadmap, we have expansion for GPU families. We've been targeting the Blackwell architecture. We want to backport this to other architectures as well, and then give you more tooling. Turns out that debuggers don't handle multi-threaded work very well, so we're fixing that. We're also working on things like FP4 and arbitrary size tiles and so forth. And thank you for listening. As a free gift, you can have a self-paced course on DevZone at NVIDIA.com. Any questions?
Yeah, we can take questions now. Oh.
I guess I have a hardware question, so forgive me if I'm wrong, but it seems like NVIDIA is focused on threads in the GPUs and not devoted NPUs. Is there any plan to start making NPUs for lower energy-intensive applications?
Yeah, I'm not in hardware. I mean, NPU is I think a different. I mean, I think that's an Intel product line, but tensor cores are more our version of like the NPU, if you will. So, but I can't comment on like any future hardware operations.
If this is working well, do you see yourself moving some of your kind of long, hard-to-write libraries so they're rewritten in this and you have something that's more maintainable?
Yeah, I mean, that's the plan. We should be eating our own dog food very quickly. Of course, we have hundreds of thousands of kernels written in SIMT threading today. And you don't need, not everyone needs them. So, and the other thing is like, we're still working with researchers on like what maps to the MMA, the tensor core is the best. So if you come at me with a tree algorithm, I don't have a mapping to a tensor core yet. So the SIMT coding still is very viable, and to get the maximum performance, you're still going to need some of those things as well. And so we're hoping we can move to this new paradigm and everything be much faster, but at the same time, it's a step-by-step process. But yeah, I do work with a lot of library teams all working on using tile as much as possible. All right, thank you very much.
Thank you so much, Andy.